This lecture is going to be a bit different from our previous lectures in that I've got the notes all written out. It actually took me hours to do this, and so rather than rewrite them, we will cover this in a little bit more speedy manner. The other reason for that is that a lot of this is just pushing the math through to get this to all work out. And so while it's important that it's there, I thought that this is material that we could go through a little bit more quickly and get to the important conclusions. So to start out with, we have proven that the LMS adaptive filter, with the appropriate choice of mu and a few assumptions, converges in the mean. That means that on average, the weights from the LMS adaptive filter will be the weights that you would get if you solved the Wiener-Hopf equation directly. However, because these weights are continually updated, and they're continually updated based on a noisy gradient, they're going to bounce around. So on average they may be correct, but at any given point in time, even after convergence, they will still be bouncing around the true solution. We want to figure out how much that is going on. And so we're going to start actually by looking at the mean squared error of the output. And we're concerned with the excess mean squared error. So the excess mean squared error is defined as the total error that we expect minus the minimum error that we cannot predict. And that's based on our previous analysis of error in the Wiener-Hopf solution. Okay, so this first page of notes is actually mostly going to be laying the groundwork. The first is, recall that by orthogonality, we have that the error at any given sample is going to be orthogonal to the input. That is, in the expectation, the expected value of the error times the input is going to be 0. So we're going to define a new quantity that will be quite useful. That is the error that we would get if we had a perfect estimator. So Vn is equal to d minus the optimal weights times our current input. We can then rearrange this equation to write that d, our target signal, is defined as the part that we cannot predict using xn plus the predictable part of dn based on our optimal filter and x. So the variance of this, the expected value of v squared, is going to be it's our E min, right? Because this is defined as the error that we cannot predict, the only error that will come out when we have an optimal filter. And that's sigma d squared minus r dx, r transpose rx r dx. So this expression right there. Okay? Well, Vn is uncorrelated with Xn. That's by construction. But we're also going to make some assumptions here. You'll find that when we're dealing with time-varying signals and systems like this adaptive filter, we often have to make assumptions. We will assume that Vn is independent of Xn. Now, uncorrelated is easy to show. Independence is a little bit trickier, but it's not too much of a stretch to believe that it would be independent. We're also going to assume that it's stationary and that it's white. Furthermore, we're going to assume that all the signals are zero mean. So we can rewrite the total error as, starting with our definition of the error, d minus our filtered output. And when we express our filtered output in terms of Vn, then we get this extra V or W opt term that shows up in there. And so we get essentially that our error is equal to the error that we get because we have no way, even with an optimal filter, of predicting what that is. And we also have the excess error. This is error that we could have done better with had we had the optimal weights. And that's defined as, or it comes out as the delta W, if you will, times x of n. So the unavoidable error, Vn, and the excess error are independent. So when we find the mean squared error of this, remember that's where we're going eventually, we get the expected value of this mean squared error is equal to our E min, which is the variance of our unpredictable or unavoidable error, plus the expected value of the excess error squared. Okay, so now the next page of notes, we're going to start to wander into just a lot of algebra. And to facilitate this, we're going to define another term. We have our excess error. We're going to define another error, and this other error is defined as in the same way as our excess error, but it's based on an updated weight. To calculate or get an expression for this in terms of our excess error, we can simply plug in the equation for the weight update into our delta W n plus 1, and we get that this new error relationship, which the P is for posteriori error and the A is for a priori error, I'm sorry. And so we have the posteriori error is given as the a priori error minus this mu times the error times, we end up getting the norm square of our input vector x. So this shouldn't come as a surprise. What it's saying is that if we can update our weights based on the current output sample, you would expect them to be a little bit better. You would expect our error to decrease, and that's what this is showing. Okay, so using this relationship that we've just developed and solving for En, and then we plug that back into our weight update equation, we get a term, an expression here that shows that our weight misadjustment at time n plus 1 is equal to the weight misadjustment plus, here we have our x vector divided by its norm square times the difference between these two errors. This isn't that meaningful, but one thing that is meaningful is that we can rearrange it and notice that our mu is completely gone. A lot of this is just work so that we can get terms that are useful for us as we work our way back to getting a good expression for the expected value of the excess error squared. So the first thing we're going to do before we take the expected values is we will find the norm square of both sides. And when we do so, we do that by taking these vector quantities and multiplying the transpose of the left side by the left side and the transpose of the right side by the right side. We'll get a bunch of terms. And note that delta Wn plus 1 times x is equal to EP. Likewise, delta Wn times x is equal to EA. We've defined those previously, so now we can get rid of some of these terms and simplify. And we end up getting cross terms that are equal on both sides. So removing those, we now get a expression that has to do with the errors normalized and the norms of our weight vectors. Once again, probably not that interesting. However, in the textbook that I got this from, it makes a big note of the fact that there's some conservation of energy going on between our weight updates and our errors. But we're now getting closer to a solution. Now we're going to take the expectations and we're going to assume steady state. So for us, we'll say that a filter is operating at steady state if the expected value of our misadjustment of the filter goes to a constant, and usually we want that constant vector to be 0. And we showed that for mean squared convergence, that indeed is 0. And also that the variance of the weights, of the weight misadjustment rather, goes to a constant. This would be a constant matrix. This is a autocorrelation matrix on the misadjustment of the weight values. Okay, so when we take the expectation of both sides and the fact that, let's put it up here, the expectation of this term and this term should both become constants, some constant matrix C, we can cancel that from both sides. As a result, we just have the expectation of the EA term and the EP term. And just as a reminder, this applies as n goes to infinity. Time to do another substitution. We have come up with an expression for E in terms of EA, and that was up above, I think the first thing at the top of the page. So we'll use that and plug it into the right side of our equation here. And it's starting to look ugly, but everything kind of works out. First, we note that this EA squared term is the same as this one. So those cancel from both sides. That leaves us with just two terms. In the first term, the norm of x squared, norm squared of x, cancels. And in the second term, it at least cancels part of it. We have a square on the bottom and a to the fourth power on the top, leaving us with a mu times the expected value of the error squared times the norm squared of x is equal to 2 times the expected value of the excess error times the error. Once again, this is as n goes to infinity. So we're in the closing stretch here, and we have one more page of detailed notes to go through. Copying the equation from the previous page up top, I've labeled the left-hand side and the right-hand side to make it convenient. And we'll do another substitution. Remember that En is equal to Ea, our excess error, plus V, our unavoidable error. And also reminding you that our assumption was that Vn is independent of x and Ea. So based on this assumption and this substitution, on the left-hand side, we can simplify things. We will get cross terms with EA and V, and they'll go away, leaving us with just the expected value of the norm squared of x times our excess error squared, plus the energy or the power, the variance in V, times the norm of x squared. Note that sometimes we'll flip back and forth, and now I think is one of those times where we will take the expected value of the norm of x squared and substitute another expression for it, which is just the trace of the autocorrelation matrix. If you write out both expressions, you'll see that they are trivially equal. So now looking at the right side of this equation and doing the same type of a thing, we assume, of course, that V and E are independent and that they have a correlation of 0. So that goes away, and all we're left with is 2 times the expected value of EA squared of n. Well, the expected value of EA squared is our excess mean squared error. This is wonderful because we are trying to solve for excess mean squared error, so all we have to do is figure out how to simplify the expression that we have here. Rearranging the terms now, we have that the expected mean squared error is equal to mu over 2 times the expected value of the norm of x squared and EA squared, plus terms that we can actually analyze. Mu over 2 times sigma v squared times the trace of Rx. So we really can't calculate the expected value of the norm squared of x times EA squared. So we're going to have to approximate that. But before we do, a few things to note. One, mu shows up in 2 places here. It's multiplying the entire excess mean squared error expression. So even if we know nothing else, we know that we can decrease the excess mean squared error by making mu smaller. There's, of course, another problem with making mu smaller, is it means the adaptation goes slower. There's an optimal mu for the speed in adaptation or convergence, and so it's a trade-off then. How much excess mean squared error can we handle, and how fast do we want this to converge? As you might be anticipating, later we're going to talk about a variable step size where we have a larger mu until the system converges near an optimal value, and then we squeeze mu down so that the excess mean squared error is going to decrease. Okay, so how do we approximate that value? Well, if EA is small enough, and this can happen if we have a very small mu, because the EA represents the misadjustment error, and with a small mu we've just shown that we can adapt. So we're going to assume that EA is small. So with a very small mu, the first term in our expression is going to be much smaller than the second. And so we can just approximate the excess mean squared error for a very small mu as mu times the variance or energy of our unavoidable error times the trace of the autocorrelation of our input, all divided by 2. Well, having this trace of our autocorrelation of our input tells us something else. It tells us that the larger our x vector is, in other words, the larger the filter is, the larger that value is going to be, and the larger our excess mean squared error is going to be. So we can anticipate another trade-off here. If a large adaptive filter did a very good job of modeling some unknown system or doing a good prediction because of its size, we can decrease the error But on the flip side, and we would decrease the error by perhaps being able to predict d better. In other words, sigma v squared is going to decrease. But at the same time that sigma v squared is going to decrease, the trace of Rx is going to increase. So we have this tension here. And we'll see this type of thing multiple times. We'll come back to it. So let's assume now that mu was small enough that the filter converged, but not small enough that really the first term was significantly smaller than the second term. Well, we'll do a different approximation here, and that is we're going to assume that the expected value of the norm of x is somewhat uncorrelated with the excess error, or the expected value of the excess error. And this actually is not too bad of a proof. Why would this not be true? Well, x has a direct impact on the weights, which has a direct impact on E. So E is really a function of our x, but E is going to be changing slowly. EA is going to be changing slowly. And so it does make sense to say the expected value of our current x vector really won't have a large impact once we've converged on the excess error. And so we're going to say that that expectation is equal to the product. Simulations of real systems have shown that while this isn't perfectly true, it's a reasonable assumption and the difference isn't too great. Okay, now that we've got this term out there by itself, we recognize it again as the excess mean squared error. So going back to this equation for excess mean squared error and making this approximation that we just made and the substitution of expected value of EA squared being expected mean squared error, we now get this approximate equation down here, right here. Solving for LMSE now gives us this very useful expression. It determines a lot of what we will do when we're determining mu and characterizing how things adapt. So in this expression, mu shows up in the numerator, so as mu decreases, so does our excess mean squared error. It also shows up in the denominator. So in order to keep this from blowing up, we want to make sure that mu times the trace of Rx, which by the way is also the sum of the eigenvalues of Rx, is not anywhere near 2. It needs to be below that. So as mu times the trace of Rx approaches 2, then we have 0 in the denominator. This expression blows up. So it also tells us that we can choose mu now to be, we'll use a different form and we'll find this useful later, to be 2 times some variable beta divided by the sum of the eigenvalues or the trace of x or Rx Rx. And the beauty of using this beta function or beta value instead of the mu is that mu has all these constraints based on the eigenvalues. But in general, you can say, I want a filter to have so much excess mean squared error or to adapt at such and such a speed, and beta is kind of like a universal parameter that's independent of the particular characteristics of your filter. and you want to pick beta less than 1. In practice, I often pick beta to be somewhere between 0.05 and 0.5. That tends to work quite well. Okay, so the takeaways here are that the excess mean squared error is directly a factor of our mu's, which we can now express in terms of this beta, if we like, and the beta will give us something that now looks like this, where the trace of Rx, or the sum of eigenvalues, is cancelled out, and now it's purely a function of beta and the unpredictable or unavoidable noise energy sigma v squared, which is also our E min.